Welcome! In this session, we'll tackle LeetCode problem number 693, titled Binary Number with Alternating Bits. This is a great problem to strengthen your understanding of binary representations and bitwise operations. Let's dive in and explore the problem in detail. In this problem, we are tasked with determining whether a given positive integer, n, has alternating bits in its binary representation. A number is said to have alternating bits if the sequence of bits in its binary form alternates consistently between 0 and 1, or 1 and 0. For example, the binary number 101 alternates between 1, 0, and 1, so it satisfies this condition. However, the binary number 111 does not alternate, as it has consecutive ones. The input to the function will be a single integer n, which lies within the range of 1 to 2 to the power of 31 1. The output should be a Boolean value, true if the binary representation of n has alternating bits, and false otherwise. To help clarify the problem further, let's look at a few examples. In the first example, the input is 5. The binary representation of 5 is 101, which alternates perfectly between 1, 0, and 1, so the output is true. In the second example, the input is 7. The binary representation of 7 is 111, where all bits are consecutive ones, meaning it does not alternate, so the output is false. Similarly, in the third example, the input 11 has a binary representation of 1011. While it starts with an alternating pattern of 1, 0, and 1, the last two bits are both 1, breaking the alternating pattern. Therefore, the output is false. Finally, in the fourth example, the input is 10, which has a binary representation of 1010. This alternates consistently between 1, 0, 1, and 0, so the output is true. Now, let's consider some constraints and edge cases. First, the input integer n is guaranteed to be a valid positive number within the range of 1 to 2 to the power of 31 1. One edge case is the smallest possible input, n equals 1, where the binary representation is simply 1. Since there's only one bit, it's considered to have alternating bits, and the output should be true. On the other hand, the largest possible input, n equals 2 to the power of 31 1, has a binary representation of 31 consecutive ones, which clearly does not alternate, so the output would be false. Another interesting case is when n equals 42, where the binary representation is 101010. This alternates perfectly between 1 and 0, so the output is true. However, for a number like n equals 3, the binary representation is 11, which does not alternate, and the output should be false. It's also worth noting that the problem encourages you to use bitwise operations to efficiently analyze the binary representation of n. These operations are more computationally efficient than converting the number to a string and analyzing it character by character, so keep that in mind while designing the solution. To solve this problem, one straightforward way to verify if a binary number has alternating bits is by checking each bit individually. This is known as the brute force approach, where we compare each bit to the one before it. If two consecutive bits are the same, the number fails the condition. To implement this, we use bitwise operations like right shift to extract each bit and bit masking to isolate it. By iterating through the binary representation of the number, we compare the current bit with the previous one. If all bits alternate correctly, the number satisfies the condition. While this approach has a time complexity proportional to the number of bits in the number, which is O log n, it also has a constant space complexity. However, manually managing each step of the bit manipulation can be error-prone and less efficient compared to other methods. This is why we turn to a more optimized solution for a cleaner and faster implementation. A more efficient way to solve this problem is through an optimized approach that utilizes XOR and bit manipulation. The key insight here is recognizing a unique pattern in numbers with alternating bits. For example, if n is 5, its binary form is 101, which alternates perfectly. Similarly, for n equal to 10, the binary form is 1010. When a number like this is right-shifted by one position and XOR'd with itself, the result is a number with all bits set to 1, such as 111 for 5 or 1111 for 10. This happens because XOR highlights differences between adjacent bits, and alternating bits ensure this pattern. To verify this result, we use the property that a number with all ones in binary satisfies x and x plus 1 equals 0. This eliminates the need for iterative comparisons. The steps are straightforward: compute n XOR n1, and then check if the result meets the condition. This method is highly efficient, with constant time and space complexity, because it relies on just a few bitwise operations. This optimized approach offers several advantages that make it the preferred solution. First, it is highly efficient, running in constant time and space, which is especially important for large input values. Second, it is elegant, as the use of XOR in bitwise operations eliminates the need for manual iteration or complex logic. Lastly, it is scalable, with no additional adjustments required for edge cases like very large numbers. The breakthrough insight here is the XOR operation's ability to create a number with all bits set to 1 when the original number has alternating bits. This, combined with the property x and x plus 1 equals 0 to verify the result, forms the foundation of this approach. These observations not only simplify the implementation but also ensure that the solution is robust and efficient. When comparing the two approaches, we can see clear trade-offs. The brute force approach is conceptually simpler, as it involves straightforward bit-by-bit comparison. However, it is less efficient and requires more manual bit manipulation, which can make the implementation error-prone and harder to optimize. On the other hand, the optimized approach is slightly more complex to derive, as it relies on key insights about XOR and bit manipulation. However, it is significantly faster and cleaner in implementation, with constant time complexity and greater scalability. In conclusion, the optimized solution is the superior choice, as its efficiency and elegance make it ideal for handling both typical and edge case inputs, ensuring a robust and high-performing implementation overall. The goal of this problem is to determine if a given integer, when represented in binary, has an alternating bit pattern. An alternating bit pattern means that no two adjacent bits in the binary representation are the same. For instance, the binary representation of the number 5 is 101, which alternates between 1 and 0, so it meets the condition. On the other hand, the binary representation of 7 is 111, where adjacent bits are the same, so it does not meet the condition. The first step in solving this problem is to convert the given integer into its binary representation. In many programming languages, like Python, this can be done using a built-in function such as bin, which returns a binary string prefixed with 0b. By ignoring the prefix and focusing only on the sequence of binary digits, we can analyze the alternating pattern. For example, if the input is 5, its binary representation is 101, which becomes our focus for validation in the subsequent steps. Once we have the binary representation of the number, the next step is to iterate through the sequence of binary digits and check if the alternating bit condition is satisfied. This involves comparing each bit with the one immediately following it. If at any point two adjacent bits are the same, the number does not have alternating bits. Mathematically, the condition for alternating bits is that the current underscore bit must not equal the next underscore bit. If this condition is violated, we can conclude that the number fails the test. For instance, consider the binary string 101 from the number 5. First, compare the bit at index 0, which is 1, with the bit at index 1, which is 0. Since they are different, we continue. Next, compare the bit at index 1, 0, with the bit at index 2, 1. Again, they differ, so the pattern holds. If no violations are found after traversing the entire binary string, we return true, indicating that the number has alternating bits. Otherwise, we return false. To deepen our understanding, let's look at some key insights and edge cases for this problem. First, the definition of alternating bits simplifies our task. Consecutive bits must alternate between 1 and 0. This means the solution only needs to compare adjacent bits in the binary string. Second, every integer has a unique binary representation, so the problem boils down to analyzing this specific structure. Now, consider edge cases. Single-bit numbers such as 1, 1, or 0, 0 always have alternating bits because there are no adjacent bits to compare. Numbers with all bits the same, like 7, 111, fail the condition immediately since adjacent bits are identical. Finally, for large numbers, the algorithm remains efficient because the length of the binary string is logarithmic relative to the input value. The only data structures we need are the binary string for visualization and a simple loop to traverse and compare adjacent bits, ensuring the algorithm remains straightforward and scalable. Analyzing the complexity of this algorithm, the time complexity is O(k), where k is the number of bits in the binary representation of the input number. Since the number of bits is proportional to the logarithm of the input value, the time complexity can be expressed as O log n. For space complexity, storing the binary string requires O(k) space. However, there is an optimization that avoids string manipulation altogether and works directly with bitwise operations. In this optimized approach, the number is XOR'd with its right-shifted version. If the binary representation of the result is a sequence of ones, the number has alternating bits. To verify this, check whether the result ANDed with itself increment by 1 equals 0. This formula ensures that the result is indeed a sequence of ones. By avoiding the need to convert the number into a binary string, this approach is more efficient and works directly with the binary representation at the bit level. Let's walk through two examples to solidify our understanding of the algorithm. First, take the input n equals 10, whose binary representation is 1010. Starting with the first pair of bits, compare 1 with 0. Since they differ, move to the next pair, compare 0 with 1. Again, they differ. Finally, compare 1 with 0, and they differ as well. Since all comparisons satisfy the alternating condition, the result is true. Now consider the input n equals 7, whose binary representation is 111. Compare the first two bits, 1 and 1. They are the same, which violates the alternating condition. This means the result is false. These examples illustrate how the algorithm checks for alternating bits by systematically comparing adjacent bits in the binary representation. This implementation determines if a given integer n has alternating bits in its binary representation. The hasAlternatingBits function is part of the solution class. First, the binary representation of n is computed using Python's bin function, and the 0b prefix is removed by slicing with the 2. This creates a string of binary digits. Next, the function iterates through the binary string, comparing each bit with the one following it. If two consecutive bits are identical, the function immediately returns false, indicating that the binary number does not have alternating bits. If the loop completes without finding any identical consecutive bits, the function returns true. This approach ensures that the function efficiently checks the alternating bit condition, as it stops as soon as a violation is detected. The algorithm is straightforward and leverages Python's string manipulation capabilities for clarity and simplicity. The time complexity is O(k), where k is the length of the binary representation of n, and the space complexity is O(k), due to the binary string storage. This is the Java implementation of LeetCode problem number 693, binary number with alternating bits. The solution mirrors the Python logic, converting the given integer to its binary string representation and checking for consecutive identical bits. Java-specific differences include the use of integer to binary string for conversion and explicit type declarations. The loop iterates through the binary string to verify the alternating pattern. To understand the problem, let's go through some examples. For the first example, we are given n equals 5. The first step is to convert this number into its binary representation. Using the expression bin 5, 2, we get the binary string 101. Now, we need to check whether this binary string has alternating bits. This means we need to ensure that no two consecutive bits are the same. Starting with the first pair of bits, at index 0, we see that the first bit is 1 and the second bit is 0. Since they are not the same, we proceed to the next pair. At index 1, the second bit is 0 and the third bit is 1. Again, these are not the same. After checking all pairs, we find no consecutive identical bits in the binary representation. Therefore, the function returns true for this input. Now, consider a second example where n equals 7. The binary representation of 7 is 111. Let's check this string for consecutive identical bits. Looking at the first two bits, at index 0, we have 1 and 1. Since these are the same, we can immediately conclude that the binary representation does not have alternating bits, and the function returns false without needing to check further pairs. Now, let's examine a third example where n equals 10. Converting 10 to binary using bin 10, 2, we get the string 1010. Our goal remains the same, to ensure there are no consecutive identical bits. Starting with the first pair at index 0, the first bit is 1 and the second bit is 0. These are different, so we continue to the next pair. At index 1, the second bit is 0 and the third bit is 1. Again, these are different, so we move to the final pair. At index 2, the third bit is 1 and the fourth bit is 0. These are also different. Since we have checked all pairs and found no consecutive identical bits, we can confidently return true for this input. This example demonstrates that the function correctly identifies binary strings with alternating bits. To analyze the time complexity of this solution, let's break it down step by step. First, the bin in function is used to convert the input integer n into its binary representation. The number of bits in this representation is proportional to the logarithm of n to the base 2, so this operation takes log n time. Next, we perform string slicing with bin n2 to remove the 0b prefix. The slicing operation depends on the length of the binary string, which is also proportional to log n. After that, the for loop iterates through the binary string, comparing consecutive characters. The number of iterations corresponds to the length of the binary string, which is again log n. Within each iteration, the comparison operation is constant time, or O1. Lastly, the return statement is executed in constant time, or O1. When we put this all together, we see that the loop is the dominant factor, and the overall time complexity is determined by the length of the binary representation, which is proportional to log n. Now, let's consider the total time complexity and space complexity of the solution. As we've seen, the loop through the binary string, the binary conversion, and the slicing operation all contribute log n time complexity. Since these operations dominate, the overall time complexity of the solution is log n. Shifting to space complexity, the key factor here is the storage of the binary string. The binary representation of n is stored as a string, which requires space proportional to its length, or log n. Additionally, the for loop uses a constant amount of space to store the loop variable and any intermediate results of comparisons, which contributes O1 space. Finally, there's a small constant amount of space used for function call overhead in the return value, which is also O1. The dominant contributor to space complexity is the storage of the binary string, so the total space complexity is log n. To summarize, the total space complexity of the solution is dominated by the binary string storage, making it log n. This aligns with the time complexity, which is also log n. Comparing this approach to a brute force method, a naive solution could involve directly analyzing each bit of n using bitwise operations. While this would still result in a time complexity of log n, because the number of bits is proportional to log n, such an approach might involve more complex and less intuitive logic. In contrast, the current solution leverages Python's built-in bin function, making it both clear and efficient. Looking at best, average, and worst-case scenarios, the best case might occur if the loop terminates early due to consecutive identical bits being detected. However, the binary conversion still dominates the overall complexity, so all cases effectively result in log n. This insight highlights that the solution is optimal for analyzing the binary representation of numbers, as the problem inherently requires log n operations for both time and space complexities. In this problem, there are a few common mistakes that can trip up even experienced programmers. First, ignoring edge cases like n equals 1 is a frequent issue. For example, the number 1 is just a single bit, but it still qualifies as having alternating bits. Overlooking such trivial inputs can lead to incorrect results, so it's crucial to test both the smallest and largest inputs within the constraints. Another mistake is misunderstanding what alternating bits actually means. Some assume it simply means no consecutive ones or zeros, but that's not enough. The entire sequence must alternate between 1 and 0 for the whole number. To avoid this, ensure your solution explicitly enforces this alternating pattern. Finally, assuming a fixed bit length can be problematic. Hard-coding solutions for a specific length, such as 32 bits, might fail on inputs of varying lengths. Instead, your solution should dynamically adapt to the binary length of n to handle all possible inputs correctly. Another source of errors is incorrect binary conversion. If you don't convert n to binary properly, such as by using the wrong base or misinterpreting the result, your checks for alternating bits will be invalid. To address this, use reliable functions like bin, n, in Python or integer to binary string, n, in Java to ensure accurate conversion. Additionally, overcomplicating the problem can lead to inefficiencies. Some solutions involve unnecessary loops or string manipulations that increase the time complexity. Instead, consider using bitwise operations, which are not only more direct but also significantly faster. These operations allow you to work with the binary representation of n efficiently without converting it to a string. When preparing for interviews, there are a few key insights to keep in mind for this problem. Recognizing patterns is essential. Alternating bits produce predictable sequences like 101010 or 010101. Identifying these patterns can help you simplify your logic and avoid unnecessary complexity. Bitwise operations are another important tool here. They're faster, more elegant, and often preferred in technical interviews over string-based approaches. Interviewers may even ask about them specifically. Testing edge cases and extreme values is equally important. For example, testing the largest possible value of n for a given constraint ensures your solution is both efficient and robust. Finally, be prepared to explain trade-offs in your approach. If you choose bitwise operations over a string-based solution, be ready to discuss why it's more efficient and how it avoids potential pitfalls. For further practice, there are several related problems on LeetCode that can help you strengthen your understanding of binary manipulation. For example, LeetCode 190, Reverse Bits, focuses on bit manipulation techniques. LeetCode 231, Power of 2, tests your understanding of binary patterns. Of course, LeetCode 693, Binary Number with Alternating Bits, is the direct problem we're working on here. Lastly, LeetCode 338, Counting Bits, is another related problem that deals with efficient computation using binary manipulation. If you're exploring alternative approaches, a brute force method involves converting n to its binary representation and then checking whether adjacent bits alternate. This is simple to implement and has a time complexity of O log n, but it's less efficient compared to bitwise operations. A more efficient approach is to use bitwise operations, such as XOR combined with a right shift. For example, you can check if n has alternating bits by verifying that n XOR n1 results in a number with all ones in its binary representation. This method is highly efficient, with a constant time complexity of O1, though it does require a strong understanding of bitwise logic. Another alternative is the mathematical approach, where you repeatedly extract digits using modulo and division while comparing adjacent values. This method has a time complexity of O log n, and is easier to explain conceptually than bitwise operations, though it's slightly less efficient. Choosing the right approach often depends on the context, such as whether you prioritize simplicity or performance. Great job! We've successfully explored the problem and broken down its solution. Remember, mastering bitwise operations is key to solving similar problems efficiently. Thanks for watching, and don't forget to subscribe for more insights into coding challenges. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!